Let's take a moment to really understand the effect of contention on a distributed system. It actually does have a very dramatic effect. It has a great impact on the scalability of the system, for example, and we're going to explore that in detail. So the first thing we have to recognize is that any two things that contend for a single limited resource are in competition with each other. That competition can only have one winner. You can't have them both win. That's not how contention works. This means that the others are forced to wait in line for the winner to complete. Now, a way to think about this would be to think about an office, for example, where you have a photocopy machine. Now, if you have multiple people waiting in line to use that photocopy machine, only one person can use it at a time. The first person who gets there gets to use it. Everybody else stands in line behind them. Now, of course, if the line is small and the people are doing very small jobs, this isn't really a big deal. You'll go through the line very quickly. But as the line gets longer or as those jobs get bigger, it starts to become a larger and larger problem. As the number of things competing for that copy machine increases, the time to free it up increases as well. So what ends up happening is maybe the first person takes a minute to use the copy machine, the second person takes a minute, the third person takes a minute. Each of them is only taking 1 minute to use the copy machine. But if you're the 10th person in line, you're waiting at least 9 minutes before you get your turn. And so eventually, as that line gets longer and longer, we'll exceed any sort of acceptable time limit. And this happens in software as well. When we contend for any particular resource, we're going to end up with these lineups. And as those lineups get longer and longer, the time to free up those resources becomes unacceptable. We start to get into things like timeouts in our system or users leaving because they're waiting too long. And that's the problem that we're trying to address here. Now, how does that affect scalability? Well, there's something called Amdahl's law that illustrates this. So Amdahl's law defines the maximum improvement gained by parallel processing. So in any particular system, there is going to be pieces of the system that can be parallelized and pieces that can't. When you have a single limited resource that has contention around it, then you can't parallelize that. That's something that only one person can use that thing at a time, or only one piece of your system can use that thing at a time. And as a result, everything else has to wait in line. Now, what Amdahl's law shows is that improvements from parallelization are limited to the code that can be parallelized. So if you have pieces that can be parallelized, you can improve those. The pieces that can't be parallelized, though, there's nothing you can do about it. You can add more resources, you can throw more concurrency at it, you can create new pieces of hardware and deploy your system to multiple locations, but it doesn't matter because you have that single limited resource that you are contending for. And so no matter how much you parallelize, it's going to make no difference on that piece that can't be parallelized. Contention then limits parallelization and reduces the improvements. And so you can see on our graph here, we're graphing throughput versus concurrency. Now, in an ideal world, we would have linear scalability, in which case we have that dotted line, which really is a fantasy because at some point in your system, there is always going to be some sort of contention and there's no way to eliminate it. But we can try to reduce it. Now, what we find, though, is that if you look on the bottom where we have concurrency, we are increasing the number of pieces of the system that are processing data, essentially. So we're increasing the concurrency in the system. And what we see is that because of contention, we have diminishing returns. We start out, maybe we double the number of machines or the number of processors or whatever, and we see a nice improvement. And so then we think, well, we'll double it again and we should get, the same kind of improvement. But as it turns out that when we double it again, it actually is a little less than we expected. And so then we double it again and it's even less than we expected again. And this happens over time to the point where we start trying to improve the concurrency and we notice we're not really seeing any benefit anymore, or we're seeing very little benefit. And that's all because of Amdahl's law. And essentially what happens is we have a bunch of things contending for that one limited resource that can't be parallelized, and everybody gets stuck waiting in line. And that's what reduces our ability to parallelize things.